So we're going to look now at the set of attractors that a system may display over long term. And with that, we're also treating of transients and initial conditions. Transients are the various paths taken initially before two trajectories converge on an attractor. And initial conditions are, of course, our starting point. Imagine the ball rolling in the surface that's shown there. We could start it from the same position, but with two different initial velocities. So that's two different starting conditions. And you can see there are quite distinct transients, but the ball will end up more or less in the same place. So we're distinguishing in transients and attractors between short-term behavior and long-term behavior. And given a specific set of parameters, let's hold our system steady, and a set of initial conditions, we can watch the system to see where does it go. And some things are clear. A rolling ball will come to rest at the bottom of a hill. That's an obvious attractor, and it's unlikely to be, and nothing else will result. In a frictionless ideal mass spring system, so totally in the world of models, of idealized models, it will oscillate regularly and there will be no change. There's no attractors actually in such a system. If it's driven, if we have a source of energy, we may get oscillation. But we see many other kinds of long-term behavior, including the kind of behavior we're familiar with from the weather, which is chaotic in a very specific sense, which we will dig into a little bit. So it's non-random, but it's also, in a very specific sense, non-predictable. And deterministic dynamic systems provide us with a really good tool for making the world intelligible, but they do not give us unlimited predictive powers. So how do we formalize the notion of an attractor? Well, if over the long term, the system occupies only a limited part of its state space, so there's many states it could occupy, but over the long term it's restricted to some specific volume of the state space, and if when it's perturbed to another part, it goes back to that specific volume, then we have an attractor. The restricted volume in which to which the system tends is the attractor. And there are exactly three kinds of attractors. The point attractor is a single point in state space, and trajectories will all converge to that single point in state space. We've seen this with the pendulum, where the state space was given by the position within a circular state space and velocity, and in the presence of friction, such a system will run down and stop. The pendulum will always come to a rest. In this sense, death is the ultimate point attractor. A plucked string displays the same dynamic. If you pluck the string on a guitar, it will oscillate, but those oscillations will gradually dampen, decay, and the string will come to rest. So point attractor is very simple. The next kind of attractor is called a periodic attractor or a limit cycle attractor. And you can see an example there in the state space where trajectories that begin within the ellipse develop outwards and land on the ellipse, develops from the trajectories that start outside the ellipse, veer inwards, and in both cases they land on the same elliptical path here, the limit cycle attractor. Any system that displays a limit cycle behavior can be called an oscillator, and we find oscillators throughout nature. We see limit cycle attractors, of course, in motions of the planets. We find these kinds of dynamics in pulsing of neurons, in heart tissue. Biological systems are absolutely full of pulses of limit cycle dynamics. And when we're speaking of these kinds of dynamics, we often want to refer to where something is in its cycle, and we said that the term phase has this distinguished meaning. It has other meanings, but this is a distinguished meaning of the term phase, which means whereabouts are we in the cycle. And we noted that describing where you are in a circle can be done in various ways. So phase may be a number between 0 and 1, or between minus pi and pi, or between 0 and 2 pi. The conventions differ as we move from one discipline to the next. Engineers have different conventions from physicists who have different, but it's probably the case that different subschools of physics have different conventions. But the underlying idea is very simple. So there's the two kinds of attractors we've looked at so far, the point attractor and the limit cycle attractor, both very simple. The chaotic attractor is not so simple. This is likewise a finite subset of state space into which the system will tend in the long term, but in this case without repetition. When we have a system that displays this is what we're going to call chaos. It's specifically characterized by a sensitive dependence on initial conditions. That means the two trajectories that start very, very close together will diverge over time, losing all mutual predictability. It's a very, very important fact. The chaotic attractor is a small part of the state space within which the system is to be found, but it does not have a simple repeating structure. This shows the Lorentz attractor, which is from one well-known set of differential equations, and the dynamicist has in their toolbox a bunch of model systems for which the equations have been well worked out, that demonstrate specific forms of these attractors. So the Lorentz system is very well studied mathematically and has provided a useful model for certain processes in nature. Dynamicists will have a bunch of attractors that they can call on. So the van der Pol oscillator, the Rayleigh, the Duffing system, there's a whole bunch of these things which are just like the Swiss Army knives of the dynamicist. Take them out when needed. And here we can illustrate the evolution of two trajectories within a system which has a chaotic attractor. It is in fact a Lorentz system. And we're going to start this system from almost the same initial conditions. So we're going to follow two trajectories, one starting at 0, 1, 0, and one starting at 0, 1.001, 0. So they're very, very similar. The two trajectories are shown in blue and red, which for the present are almost completely overlain. The bottom plot on the right-hand side shows the difference between the two trajectories, and you'll notice that the scale of the plot on the y-axis on the plot of the difference is changing in real time as we watch this. The two trajectories are still very, very, very close though. The differences between them are becoming more distinct, and now they're suddenly very large. Both trajectories lie on the chaotic attractor, but the degree to which one system is predictive of the other system has changed, and now they're essentially not predictive of each other. There are very well worked out techniques for describing quantitatively exactly how much one can predict one system from another. And the divergence here is very, very clear. And there's the attractor being rotated around so you can see its three-dimensional structure. You can see that these trajectories are not random. They occupy a very specific subset of state space, but they do not feature the kind of regularity that we see in limit cycle attractors. Chaos was a fascinating discovery in the science of nonlinear dynamics in the 20th century. Chaos in the related area of fractals and complexity theory have all sort of hugely enlarged our understanding of how the world is both unpredictable and yet law-governed at the same time. We will describe a system as chaotic if it displays the sensitive dependence on original conditions. This has been popularized, and you may have been schooled in the film Jurassic Park by Jeff Goldblum, who gave Laura Dern here a lecture on chaos, using the so-called butterfly effect, which has unfortunately been terribly misinterpreted in popular culture as if butterflies were agents of destructions. The way the butterfly effect should be understood is that the tiniest little change in a system can have enormous ramifications down the line. This was the old idea of a butterfly flapping its wings off the coast of China, leading to a hurricane somewhere else. So in chaotic systems, The present determines the future, but the approximate present does not approximately determine the future. And our knowledge of what the present is always approximate. The introduction of the notion of chaos would lead us, if we were pursuing a different route, to the difference in flows between laminar flow and turbulent flow. You're familiar with these from pouring water. If you pour water from a jug slowly, you get nice laminar flow. Turn on a tap suddenly and you get turbulent flow. The turbulence in the atmosphere is the origin of the chaos we see in our weather systems.